Okay, so we've been talking about all this energy from the chemical reactant standpoint. We've been talking about reactants going to higher energy or lower energy and saying that that is just going to go out to the environment. What I'm going to talk about in this video is what actually happens to that energy, the thermal energy of the environment. So thermal energy refers to the energy associated with the constant motion of the particles that make up a substance, but we're not talking about like the energy associated from a baseball flying through the air where the whole substance is moving as one. We're talking about the energy of the vibration of the actual molecules within that baseball. Temperature refers to the actual speed of the particles. So a basic thing that we need to know about this is a higher temperature means, in general, faster particles, and a lower temperature means, in general, slower particles. So what we're doing here then is keep in mind that this is an average over a significant statistical range. And that doesn't mean that all the particles are going faster or all the particles are going slower. It just means in general they're going faster or slower. So in a sense, this is a kinetic energy. So when an exothermic reaction happens, the energy gets released and makes the substance hotter. And in general, what that means is that these particles are actually moving faster. Okay, so the total amount of energy then associated with the temperature or the thermal energy depends on three basic things. The temperature of the substance, the amount of matter in the substance. In this case, because we're dealing with just a general substance that's not going through a chemical reaction, we typically just use mass. And the type of substance or the specific heat capacity is how we take into account the type of substance. This energy, thermal energy, is then related to the mass, the specific heat capacity, and for some reason we use C for specific heat capacity. That's the amount of energy, when we use it in chemistry, we say, required to raise 1 gram by 1 degree Celsius. And just to give you a basic idea, the C of water would be 4.18 joules per degree C. Gram. Does that make sense? Yeah, that makes sense. And the temperature of the substance. Now, we're not typically dealing with chemical reactions that are heating things up from absolute zero, cooling things down to absolute zero. So this absolute amount of energy isn't typically what we use. What we use instead is we look at changes in energy. Changes in energy we give a special name called heat and a special letter, Q. Capital Q is typically used in physics for some reason, and small q is a little bit more commonly used in chemistry. So I'm going to call it small q just to be consistent with the textbook that my class will be using to study this. Q is the change in thermal energy, ET2 minus ET1. Typically, the mass of the substance and the specific heat capacity of the substance aren't changing because we're assuming that the substance is only changing temperatures, it's not changing form. So we could call this one MCT2, and again, MC, assuming that neither one of those things change, T1. So our actual amount of heat here, or change in energy, is MC delta T. This delta just means T2 minus T1. So we could, if we wanted to write this out, MC T2 minus T1. So when we talk about all these endothermic and exothermic reactions, taking or giving energy to the environment, and we try to figure out, well, what does that really mean? This is the equation that we can use to figure out if this much energy, if this is the energy change, then this will represent the actual change in temperature. Just to keep it simple at first, I'm going to focus on just changes in temperature and assuming that we don't have any state changes. But if we had something change from a solid to a liquid or a liquid to a gas, we'd need heat to cause that change in state, and so we'd need more heat than is generally being discussed here. So again, in general, the amount of heat or the amount of temperature change that we observe in actual surroundings depends on the mass, the type of the substance, we wrap that up in the specific heat capacity, or the actual resulting change in temperature.